Cool. All right. So that wraps up the fin and extended surface discussion. And we're actually now getting to the point where we're going to, like I said, do 2D problems. Up to this point, we've talked about 1D conduction, resistances, 1D conduction, numerical and analytical for 1D conduction. And then in the last bit, we were talking about, well, we have a 2D problem, but we can approximate it as a 1D solution because we assume for an extended surface that the temperature gradient in the non-primary direction is not important. Right, so it was really a 2D problem, but we approximate it as a 1D problem and solve it that way. Okay, now we're going to get into a situation where no matter what you do, you can't accurately approximate the problem as 1D. Right? This is an actual 2D problem. And to solve these problems, before we, I guess, had relied on numerical solutions to solve this type of problem, there are limited circumstances where we can solve actual 2D problems using techniques like separation of variables. Okay, separation of variables in 2 dimensions, not just separating t and x or t and r, but now we have temperature x and y. And we have to separate out the variables there. Okay, so let's look at this example. I think the best way to walk through this is just to go through the steps in an example. So first, let's look at what we have here. We have this rectangular thing, right? And over here on the left-hand side, we're holding the temperature at some value. We'll call that 0. Now, that's a weird temperature to hold it at, but you'll see why we have to do that in a second. Let's say we're holding the temperature at the left boundary at 0. We're holding the temperature on top at TH, and then both right and bottom surfaces are adiabatic. So looking at this, you can see there's no way that this could be a 1D problem. Like there's no approximate solution where 1D is appropriate. You definitely have heat flowing in both X and Y because you're holding left-hand side and top at 2 different temperatures. So heat kind of has to go from the top surface down through the whole thing to the left-hand side. Okay. The other thing to point out is, we're assuming that it's insulated on the top and bottom, so it's actually not a 3D problem. Okay, so we have this problem we're going to try to solve is actually 2D. The process we're going to go through now, you'll have to hang with it because it's kind of I'll say it's complicated, but there's kind of a lot of subtle points that are made along the way. Separation of variables is probably one of the, I'd say, conceptually challenging things in this class. So you really want to, I think you'd want to go through this. You probably want to look at it again. You might want to read the book a little bit because it probably does a better job explaining than I can. But there's a few steps. And so we'll have to go through kind of decomposing this problem and then building it back up once we get to it. So don't get lost in the middle, in the woods, right? We'll deconstruct it and then build it back together. Okay, so let's start here. In the same way we've started every problem. We're doing conduction. We want to develop an analytical model. So let's first start by drawing a control volume. Okay, so our control volume is now, it has to be 2D. Right, so we're going to draw some rectangle. And it's not covering the full span of any one dimension because, well, it's differential in X and in Y. Okay, so this thing is, dy tall, and it's dx wide. Right? And then we have to now look at all the heat flows going in and out of this differential control volume. So let me kind of redraw this down here. So we have a little bit more room. Okay, so this is our control volume. So coming in from the x equals 0 side, we have q dot at x. Leaving, we have q dot at x plus dx. Okay, but then on the y, normally we would say that's 0. We also have heat flow coming in from the bottom, q dot y, and we have q dot at y plus dy. Right, so those are the 4 heat flows that we have now. In this problem, we're not going to have any generation or internal energy change at this point, so we'll ignore those things. This is our control volume. So let's write out the energy balance. It's what's coming in, q dot x plus q dot y. And then what's leaving? It's going to be q dot x plus dx plus q dot y plus dy. All right, so now we got to expand out our x plus dx term and our y plus dy term, as we've always done. So that becomes q dot x plus q dot y is equal to q dot x plus dq dot x dx. Sorry, I'm already making a mistake. So let's be a little bit careful here. We're now talking about a problem with temperature change in two directions, right? So when we're talking about the derivative of temperature change, it has to be, in an equation where you have two dimensions, you have to use the partial derivative to talk about the gradient in one or the other direction. So let's be careful here. So it's the partial derivative with respect to x, okay, times the differential width, which is dx, right? Not partial x. Okay, so that's in the x direction. And then in the y direction, we have q dot y plus partial q dot y, partial y dy. Right, this cancels out. Okay, and then we're left with partial q dot x times dx plus partial q dot y times dy equals 0. Okay. So now we need rate equations as we had before. We have to have rate equations for q dot, both of the q dots. So we have to apply Fourier's law for both the x direction and for the y direction. Okay, so let's say here now x. So first in the x, q dot x is equal to minus k times. I need some dimensions on here. So let's so over here we said thickness is b. Okay, and then so what is our cross-sectional area available for heat flow? It's going to be b times dy, right? That's the cross-sectional area available for heat flow for the heat that's flowing in the x direction. If that look again, so we have heat flowing this way, right? This is dy, right? So this cross-section area is going to be dy times b into the page. Okay, so minus k times b times dy times our temperature, partial temperature with respect to x. Sorry, and all of this has to be the differential. So differential with respect to x of all that. That makes sense. Okay, times dx. So we took Fourier's law, substituted in. Okay, do the same thing for the y direction. Partial with respect to y times minus k times b times now dx, right? We have to have heat flowing vertically times the partial of t with respect to y times dy. Make sure I got all that right. Okay. So now we can take everything that's constant and cancel it out. So we have minus k, we have minus k, b, canceling from both sides. We can take, right, dy with respect to the x direction is a constant. Right? That differential width in y doesn't change as a function of x. So actually dy can come outside of this differential. Or put it over here, let's say, right? So this becomes dx times dy, and this over here can come out here, and this becomes dy times dx. Right? So dx, dy actually cancels out now. Hopefully everybody sees that. So those cancel out. All right? And now we're left with the relatively simple equation. Second partial with respect to x plus second partial with respect to y, 2 is equal to 0. All right, this equation, this second derivative equation in two dimensions is called Laplace's equation. All right, that shows up all over the place, I guess. Okay, any questions on how we got this far? Yeah. Yeah, I suppose you could. I mean, you could go through and do like a BO number calculation where you're looking at conduction in the Z direction or something like that. You probably could and should do that. I guess I'm not going to go over that here, but yeah, it's something that you could do probably. The number of situations where the separation of variables is applicable, as we'll see in a second, is fairly limited, right? There's a pretty limited circumstances where it's applicable. So if you have that case show up, usually it's because it is a very, very specific case that works well for it. But that's a good question. Yeah. Okay, so Laplace's equation. Now this is our governing differential equation, right? This is the governing equation for this problem. We need to identify boundary conditions. So let's do that here as well. Okay, so our boundary conditions now, we have second derivative in two directions. So we're going to need 4 boundary conditions altogether. 2 in X and 2 in Y. So let's look first. Okay, our boundary condition in the X first, let's say Tx equals 0. If that's equal to 0, that's our first boundary condition. What's our second boundary condition in X? Well, it's the partial with respect to X, evaluated at X equals W, right over here on the right-hand side. Right, that's equal to 0. Adiabatic surface. Okay, and then in the Y direction, let's see, at Y equals 0, we have adiabatic as well. So that's dt dy at Y equals 0, that equals 0. And then our boundary condition on the top is T at Y equals, what is it? H equals T hot, TH. Okay, so we have 1, 2, 3, 4 boundary conditions for this problem. All right, this here, I'll just circle this whole thing. This here is the mathematical statement of this problem. So what I'm going to do is we've got all the statements here. We'll just kind of bring this on with us so we can refer back to it. When we talk about, write the mathematical statement of a problem, this is what you'd be doing. The governing ODE or PDE in this case, and then all the boundary conditions. Yeah.
So we're both declaring 2 different temperatures. Some equations 1 and 4, and let's set that X equals 0, Y equals 8.
Yes.
Isn't that problematic?
Yeah, it is. So you'll see, it's kind of an interesting thing that happens. But yeah, that's a really good point. So right at that corner, you see what he's talking about right up here. We're saying there's actually temperature is actually simultaneously 0 and TH at that corner. So again, like you would write the problem this way so that it's a solvable problem for separation of variables, when in reality, yeah, there's something going on here that is not purely constant temperature, right? And but you'll see there's a discontinuity in the solution right at that point.